Welcome back to this video series called Reconstructing Gravity, and this is Chapter 18 in the Gravity series called Expansion of the Universe, in which we're going to explore the hypothesis of expansion of the universe which I previously suggested. The expansion of the universe was postulated theoretically after Einstein's general relativity, but it was first measured around 1929 by Edwin Hubble, as he measured the redshift of light coming from stars and galaxies and found that the farther an object is from us, the faster it is moving away from us. And the analogy that's often used is the raisin bread. As the dough swells, the distance between the raisins becomes greater, and from observation on any raisin, that fact is true. The farther a raisin is from you, the faster it will be moving away from you. And so it's an analogy for the expansion of the universe. Here's another picture you may have seen. This is straight out of Wikipedia from the proposed Big Bang, a very rapid expansion, and this is time going to the right, size in the other dimensions. But as the matter formed and then started clumping together due to gravity, the universe expanded, and in fact, only in recent decades was it shown or measured that the expansion of the universe is accelerating. It's rather, at first they thought it was expanding, but probably slowing down. But recently it's been found to be increasing its rate of expansion, and dark energy is hypothesized as the reason for that. Cosmology is an active field of study. There is a lot going on, and there has been for the last few decades for sure. There's the Hubble telescope, the newer James Webb telescope, and a lot of other cosmological instruments are up there in space measuring things. But it should be remembered that cosmology is a vast field built upon a long string of inferences. And when you have a system like that, it's always possible, and it sometimes happens, that some fact or inference made along the way is changed by a new discovery, and then the entire stack of inferences above that have to be readapted or readjusted or just thrown out. So it's a very deep study, but it's also a sort of fragile study. Now then, what is my hypothesis about the expansion of space? Well, if you watch my other videos, I said that to make gravity work, that space has to have two components. Light space, which is the network that transmits energy at the speed of light, and dark space, which is a passive void that does not interact with energy in any way. I suggested that the tetrahedra form a light space network, and octahedra are the dark space that lies between the voids of this light space network. And the octahedra is 4 times as large, but the tetrahedron is 4 times as frequent. So in terms of total volume of space, they would always appear in equal proportion. In this model, light space would be always flowing inward towards a large mass like a star or a planet. And it would be converted on the way, it would be converted at a specific rate to dark space, which is flowing outward at the same rate, always maintaining the same ratio of light space to dark space at every location. But if large masses in the universe are essentially machines that convert light space into dark space, yet light and dark space must maintain a 1-to-1 volume proportion, then somewhere in the universe, more light space would need to be created to maintain that balance. Somewhere, but where? This might seem like a simple problem at first, but it's not. Although the conversion rate is known, it's proportional to the mass of the sun or planet involved, in the local region around that mass, the proportion of light space to dark space is balanced, even though it's being converted. And so the question is, how is this modeled in the universe as a whole? For example, the simplest possible model would be to lump all the mass in the universe in one spot and take the radius of the known universe and assume that space flows towards that one mass. And at the outer edge of the universe, there would be an escape velocity, a speed of space. And at that point, that inflowing light space would be replaced by outflowing dark space, and more light space would need to be created to maintain the balance, and that would increase the total volume of the universe. That's a very simple model, but that's an example of what I'm talking about, of how is this modeled? How could it be modeled? But obviously, all the mass of the universe is not in one place. It's distributed in a very broad sense on many scales. So what distribution of mass should be considered? Very difficult to even conceive of modeling it, but I'm gonna take a crack at a couple of things and just to get some numbers to see if there's any feasibility to this idea. Before going any further, remember, this is all speculative, but my model does have some positive features. With my model, space has a structure. It's a physical entity, not just a mathematical construct. So this is good because it provides a way for space to transform and, in a way, to grow by restructuring itself while maintaining its essential Planck length nature. It can maintain the speed of light as the total volume increases. Starting with this simplest lumped mass model, I compute the volume growth per period of time, and the cube root of that gives a linear expansion rate per time. Now, the result I got for this very simple model, 0.027 kilometers per second per megaparsec. So that's speed, kilometers per second, per megaparsec, which is a distance. A megaparsec, million parsecs. Parsec is about a third of a light year. So it's a very, very big distance. And compared to other calculations, this is a very small expansion rate, but I'll make a table later to show them all. The next model I tried was what I call uniform galaxies. Took the total mass of the universe, divided it into the number of galaxies in the universe, and gave them each of them an equal volume in the universe. Showing a 2D picture, it's really a 3D concept. The calculation result came to be 13.5 kilometers per second per megaparsec, much bigger than the lumped mass, all the universe in one place. And the other thing, I should note that in all these calcs, I used the ordinary baryonic mass, not the dark matter or dark energy mass, just the basic visible mass, which is said to be 4.9% of the total mass of the universe. So that's another unknown, another factor. But just thought I'd put that out there. That's what I used. The next calculation I tried was not of the whole universe, but just the Milky Way. Took the number of stars in the Milky Way, the volume of the disk of the Milky Way, and divided the mass of the Milky Way amongst those stars evenly. And I got a much, much larger expansion rate, 14,796 kilometers per second per megaparsec. Way bigger number, but not including the whole universe. What's the right answer for the expansion of the universe? 73.24 kilometers per second per megaparsec. I believe Hubble's original number was 71, but 73.24 is the current Wikipedia value. I got one more calculation, but first let's compare my results. My uniformly spaced, evenly sized galaxies model came the closest to the correct expansion rate of the universe, but that is in no way a correct representation of the mass distribution in the universe. So I consider this plausible, but certainly not proven. Certainly speculation. There might be something to it, maybe not, but worth a video anyways to show what I did with this. The last thing I did, just for the heck of it, although this isn't representative of anything either really, I said, well, how many stars would have to be lumped together in a mass and then given an equal cut of the universe in order to get the right expansion rate. And it turned out to be 61,350 stars per group, and dividing how much of that mass is what part of the universe, given each group an equal volume of the universe. That got me to the right expansion number. And I said, I wonder if this represents anything in reality. And there are things called globular clusters, which are, I'm reading, sized at 10,000 to millions of stars. So that globular cluster kind of fits that model, but of course they're not evenly distributed across the universe. They're found within galaxies. So just another wild shot. I think I'll wrap it up at this point. Thanks for watching. I always appreciate your interest. Please remember to like or subscribe if you're so inclined. I'll be back with more gravity talk and a summary at some point. But today we're going to head out with a musical clip from Jerry Rafferty called Get It Right Next Time.
Out on the street, I was talking to a man. He said there's so much, but there's nothing, man, that I don't understand. You shouldn't worry, I said that